Assalamualaikum warahmatullahi wabarakatuh. My name is Choirur Siwi, and in here I will explain about chapter 6, which is all about synchronization tools. The content of this chapter are background, the critical section problem, Peterson solution, hardware support for synchronization, Mutex Locks, Semaphore, monitor, and Liveness. So, objective of this chapter are describe the critical section problem and illustrate a race condition. Illustrate hardware solution to the critical section problem using memory barriers, compare and swap operation, and atomic variable. Demonstrate how multi-clocks, semaphore, monitor, and condition variable can be used to solve critical section problem. And the last one, evaluate tools that solve the critical section problem in low, moderate, and high contention scenarios. So let's start this lesson. The first one is background. Okay, process can execute concurrently, may be interrupted at any time, partially completing execution. Concurrent access to shared data may result in data inconsistency. Maintaining data consistency requires mechanisms to ensure the orderly execution of cooperating process. So, illustration of the problem suppose that we want to provide a solution to the consumer producer problem that fills all the buffer we can do. So, by having an integer counter that keeps tracks on the number of full buffer, so initially counter is set to 0. It is incremented by the producer after it produces a new buffer and is decremented by the consumer after it consumes a buffer. And here's the source code for the producer. While true, produce an item in next produce, while com equal buffer size, denoting and buffer in equal produce in equal n plus 1 buffer size and count plus plus. And this is source code for consumer. While true, and then here is a while count equal to 0, and then denoting next consume equal buffer out, and out equal to out plus 1 buffer size, and count min. Consume the item in next consume. So this is illustration of the race condition of the consumer producer problem. Counter plus plus, or the we're going to increment, the counter is used by the producer, and then the counter minus is used by the consumer. In race condition process, P sub 0 and P sub 1 are creating child process using the first system call. A race condition on kernel variable next available PID, which represents the next available process in the fire. Unless there is mutual exclusion, the same PID could be assigned to two different processes. The second material, we will talk about the critical section problem. In critical section problem, consider a system of n process P sub 0, P sub 1, blah blah blah, and P sub n minus 1. Each process has critical section segment of code. Process may be changing command variable, updating table, writing file, etc. When one process in critical section, no other may be in its critical section. Critical section problem is to design protocol to solve this. Each process must ask permission to enter critical section in entry section. May follow critical section with exit section, then remainder section. And here is the algorithm of critical section. While true, entry section, and then critical section. After that, exit section to remainder section. The solution to critical section problem. Number 1. Mutual exclusion. If process Pi is executing in its critical section, then no other process can be executing in their critical sections. Number 2. Progress. If no process is executing in its critical section and some process wish to enter their critical section, then only those processes that are not executing in their remainder section can participate in deciding which will enter its critical section next, and this selection cannot be postponed indefinitely. Number 3. Bounded waiting. There exists a bound or limit on the number of times that other processes are allowed to enter their critical section after a process has made a request to enter its critical section and before that request is granted. The next one, critical section handling and OS. Two approaches depending on if kernel is preemptive or non-preemptive. Preemptive allow preemption of process when running in kernel mode, and the non-preemptive runs until exits kernel mode, blocks, or voluntarily yields CPU, essentially free or race condition in kernel mode. The third material is Peterson solution. Peterson solution, not guaranteed to work on modern architecture. Two-process solution assume that the load and store machine language instructions are atomic, that is, cannot be interpreted. The two processes share two variables, integer turn and boolean flag array 2. The variable turn indicates whose turn it is to enter the critical section. The flag array is used to indicate if a process is ready to enter the critical section. Flag E equal true implies the process Pi is ready. And this is the algorithm for process for Pi. There is while true, flag I equals to true, turn equals to J, while flag J and turn equal to J enter the critical section, and flag I equals to false, and then enter the remainder section. Provided that the three critical section requirements are met, modal exclusion is preserved. Pi enters critical section only if either flag J equal false or turn equal I. And progress requirement is satisfied, and then the bounded waiting requirement is met. The fourth material is hardware support for synchronization. Synchronization hardware. Many systems provide hardware support for implementing the critical section code, and a processor could disable interrupts. Currently running code would execute without preemption. Generally, the inefficient or multiprocessor system, operating system using this not broadly scalable. We will look at two forms of hardware support. There are memory barriers, hardware instruction, and atomic variable. The first one is memory barrier. Memory modules are the memory guarantees a computer architecture make to application program. Memory modules may be either strongly ordered, where a memory modification of one processor is immediately visible to all other processors, and weakly ordered, where a memory modification of one processor may not be immediately visible to all other processors. A memory barrier is an instruction that forces any change in memory to be propagated or made visible to all other processors. We could add a memory barrier to the following instruction to ensure threads 1 outputs 100, thread 1 now perform, while uh, not equal to flag memory barriers and print X. Threads 2 now perform X equal 100 and then memory barrier and flag equal true. The second one is hardware instruction. Special hardware instructions that allow us to either test and modify the content of a word, or to swap the content or two words atomically. There are test and set instruction and compare and swap instruction. Here is the definition of test and set instruction. Execute atomically, return the original value of past parameter and set the new value of past parameter to true. And here's the solution using test and set function. Share boolean variable log and initialize to false. The next one is definition of compare and swap instruction. They execute automatically, return the original value of past parameter value, and set the variable value to the value of the past parameter new value, but only if value equal expected is true. That is, the swap takes place only under this condition. And this is the solution using compare and swap, shared integer log, and initialize to 0. And in here is the source code for bounded waiting method exclusion with compare and swap. Atomic variable. Typically, instructions such as compare and swap are used as building block for other synchronization tools. One tool is an atomic variable that provides atomic or uninterruptible update on basic data types such as integer and boolean. For example, the increment operation on the atomic variable sequence ensures sequence is increment without interruption. Increment and sequence. In atomic variable, the increment function can be implemented as follows. The fifth material is Mutex Locks. And previous solutions are complicated and generally inaccessible to application programmers. OS design build software tools to solve critical section problems. Simplest is Mutex Locks. Protect a critical section by first acquire a lock, then release the lock. Boolean variable indicating if lock is available or not, and calls to acquire and release must be atomic, usually implemented via hardware atomic instruction such as compare and swap. But this solution requires fuzzy writing. This lock therefore called a spin lock. This is the solution to critical section problem using lock. The algorithm is simple, just while through acquire lock and then go into the critical section. After that, release lock and go to the remainder section. This is the mutex lock definition. These two functions must be implemented atomically, and both test and set and compare and swap can be used to implement this function. The sixth material is Semaphore. Synchronization tool that provide more sophisticated way than Mutex Locks for processes to synchronize their activities. Semaphore, as integer variable, can only be accessed via two indivisible or atomic operations. They are weight and signal, originally called P and V. They are the definition of the weight operation and the signal operation. Computing semaphore, it means integer value can range over an unrestricted domain. And binary semaphore, it means integer value can range only between 0 and 1. Can solve your synchronization problem, consider P1 and P2 that require S1 to happen before S2. Create a semaphore scene initialized to 0 and can implement a counting semaphore as a binary semaphore. In semaphore implementation must guarantee that no two processes can execute the wait and signal on the same semaphore at the same time. Thus, the implementation becomes a critical section problem where the wait and signal code are placed in the critical section. Could now have abusive waiting in critical section implementation, but implementation code is short. A little abusive waiting is if critical section rarely occupied. Note that application may spend lots of time in critical section and therefore this is not good solution. Semaphore implementation with no abusive waiting. With each semaphore, there is an associated waiting queue. Its entry in a waiting queue has no data item. Value of type integer, pointer to next record in the list. To operation, there are block. It means place the process invoking the operation on the appropriate waiting queue and then wake up. That means remove one of process in the waiting queue and place it in the ready queue. So this is the source code of semaphore implementation with no busy waiting. There are the wait and signal code. The seventh material is monitors. Monitors, a high-level abstraction that provide a convenient and effective mechanism for process synchronization. Abstract to the type, internal variable only accessible by code within the procedure. Only one process may be effective within the monitor at a time. The code syntax of monitor are in below. This is the schematic view of a monitor. The condition variable, condition x and y. The operations are allowed on a condition variable. X wait is a process that invokes the operation is suspended until X signal. And X signal resumes the one of process if any, the invoke X wait. If no X wait on the variable, then it has no effect on the variable. Condition variable choices. If process P invokes X signal and process Q is suspended in wait signal, what should happen next? Both Q and P can execute in parallel. If Q is resumed, then P must wait. Options include signal and wait. P waits until Q either leaves the monitor or it waits for another condition. The second one is signal and continue. Q wait until P either leaves the monitor or it waits for another condition. Both have pros and cons. Language implementer can decide, and monitor implemented in concurrent Pascal compromise be executing signal immediately leave the monitor queue is resumed. This is implemented in other languages including Mesa, C Sharp, and Java. The monitor implementation using Semaphore. The variable Semaphore mutex initially 1 and Semaphore next initially 0 and integer next count equals to 0. This function f will be replaced by that code and mutual exclusion within a monitor is ensured. Monitor implementation condition variable. For each condition variable x, we have semaphore x same initially 0 and integer x count equal to 0. The operation x wait and x signal can be implemented as that code. The eighth material and of course the last material of the chapter 6 is the liveness. Liveness process may have to wait indefinitely while trying to acquire a synchronization tool such as a Mutex Lock and Semaphore. Waiting indefinitely violates the program and bounded waiting criteria discussed at the beginning of this chapter. And liveness refers to a set of properties that a system must satisfy to ensure process make progress. Indefinite waiting is an example of a liveness failure. The example of liveness failure is deadlock. It means two or more processes are waiting indefinitely for an event that can be caused by only one of waiting process. Let S and Q be a two-semaphore initialized to 1. Consider of P0 execute wait S and P1 wait Q. Then P0 execute wait Q. It must wait until P1 executes signal Q. However, P1 is waiting until P0 executes signal S. Since this signal operation will never be executed, P0 and P1 are deadlocked. The next one is synchronization example. This is the chapter 7. In synchronization example, there is the classical problem of synchronization. The first one is bounded buffer problem. In buffer, it can hold one item. Semaphore mutex initialized to the value 1 and semaphore full initialized to the value 0. Semaphore empty initialized to the value n. Writer's problem. A data set is shared among a number of concurrent processes. Problem: allow multiple readers to read at the same time, and several variations of how reader and writer are considered all involve some form of prioritize. And the third one is dining philosopher problem. Philosophers spend their life alternating thinking and eating. They interact with their neighbors as socially occasionally try to pick up the chopstick to eat from bowl. Share data equals to bowls of rice or data set and semaphore chopsticks initialized to 1. Kernel synchronization in Windows. User interrupt must to protect access to global resource and uniprocessor system. User spin lock on multiple processor system. Spin locking threat will never be preempted. Also, provide dispatcher object user language may add mutex, semaphore, event, and timers. And even acts much like a control variable. The timer notifies one or more threads when time expired. The special object, either signal, state, object variable, or non-signal state or thread will block. Mutex special object, there's like in the picture. In the Linux synchronization, priority to kernel version 2.6 disable interrupts to implement short critical section. The version 2.6 and later fully preemptive. Linux provides Semaphore, atomic integer, spin lock, reader writer version, or both. On single CPU system, spin lock replaced by enabling and disabling kernel preemption. The next one is POSIX Synchronization. POSIX API provides Mutex Locks, Semaphore condition variable, and widely used on Unix, Linux, and Mac OS. Java Synchronization. Java monitors Java original synchronization mechanism based on the synchronized keyword and the concept of monitor. Reentering logs, introduced in Java 5, reentering logs provide a more flexible alternative to synchronized blocks. Semaphore. Semaphore are a synchronization primitive that maintains a set of permits which control access to shared resource. Condition variable, also introduced in Java 5, condition variable provide a way for threads to wait for a specific condition to become true before proceeding. And the last one is alternative approach. There are three items. The first one is transactional memory. Transactional memory, or TM, is a parallel programming paradigm where memory operations are performed in atomic transactions to avoid inter-thread memory access conflict. And the second one is OpenPM. OpenPM is an implementation of the Open Messaging Protocol, or MP, used for parallel programming and distribution on computing systems consisting of multiple processors. And the third one is functional programming language. A functional programming language is a type of programming language that focuses on using a function as the main element for data processing and computation. Maybe that's all. Explanation from me regarding chapter 6 and 7. Thank you for watching.